All right, welcome back, AP. We have 19.3, the second and third law of thermodynamics. So remember the first law we learned in chapter 5. First law of thermodynamics, energy is conserved. So remember, you can't gain or lose energy. It has to be rearranged, and that's when we practice the equation delta E Q plus W. And then we also looked at how delta H is delta E plus P delta V. And in the end, as long as pressure was constant, it equaled heat. Okay, so how is the second and third law of thermodynamics correlated to the first? All right, well, we've already been talking about entropy. So delta S entropy. And remember, entropy is about particle movement, particle disorder. Okay, so if you have a delta S that's greater than 0, the more random it is, the more particle moves, the more it increases. If your delta S is actually less than 0, then you actually have order. You have less movement. Okay, it doesn't mean you have no movement, you just have less movement. So suppose the system changes reversibly between state 1 and state 2. So you have A makes B and B makes A, it goes back and forth, back and forth. Then the change in entropy is given by, and you have an equation, as long as temperature is constant. Well, we have a name for this. It's called isothermal. Isothermal means that something is constant temperature, just means that it's not changing. So according to the first law of thermodynamics, if something is at constant temperature, your delta E equals 0. So if it equals 0, that means your Q and your W are the same value, but opposite signs. Okay, so if we have a reversible reaction, which means we are at equilibrium, okay, and temperature is constant, so notice next to the temperature, there is no delta T next to that temperature. You take the heat, divide by the temperature. You can also correlate this to delta H over temperature also, okay? The reason why you can do that is if constant pressure also. So if you have constant pressure, you can even say the Q is also the delta H. So if you know delta H, you can simply plug it in. Two numbers, divide, done, okay? So the problem is this, is when we did units for delta H, the units for delta H, we use kilojoules, okay? Or we even use kilojoules per mole. With delta S, the units that are preferred with AP, they want joules, okay? So if you're given delta H in kilojoules, just move that decimal 3 places, but you do need to have Kelvin. So make sure if you have Celsius, add 273.15 to get to that Kelvin. So the Q reverse is the amount of heat added to reversible system. So we are adding that heat, okay? Now you can lose heat also depending if it's like endo versus exo. The word reverse means that the path, reminds us that the path between the states is reversible, okay? So like a phase change would be something that is reversible and the addition of added heat. Now, I put this in here back from chapter 11. I wanted to make sure I put it back in here so you understood this, okay? With phase changes, okay, so right here we have, we'll say this is a phase change of water, okay? Notice on the y-axis is temperature, degrees Celsius, on the x-axis is heat, okay, aka Q, okay? What do we know about water, okay? Well, when it's less than 0 degrees Celsius, we have ice. When it is 0 degrees Celsius, we are at equilibrium between ice and liquid water. Above 0, but to 99, we have liquid water. And when it hits 100 degrees Celsius, then we have a phase change between liquid going to gas. And as long as it's above 100 degrees Celsius, then we have straight vapor, straight gas. So if you notice right here, at this point in time, Below this means it's below zero. So right here, this is 0 degrees Celsius. So below zero, you're still at a solid. My temperature is increasing, and I'm also adding heat because as I go up, I increase temperature, and as I went from here to here, I have added heat. But what happens when you have a phase change? Well, on this phase, whoops, I spelled it wrong. Sorry, phase change, you actually have two phase changes. Okay, so right here, melting to freezing, am I going solid to liquid or am I going liquid to solid? Doesn't matter, but it happens at 0 degrees Celsius. Notice what is also happening. Look at temperature. Temperature is constant. Okay, so there is no change in temperature, but heat is still being applied. Okay, so we looked at this also in chapter 11. Right here, from 0 degrees all the way to this point in time, well, right before it changes to a gas, I know that this is going to be 100 degrees Celsius. I have liquid, I have increased my temperature, and I have also kept adding the heat. But when I get to a phase change for vaporization, liquid to gas, or am I cooling it down, gas to liquid, notice there is no change in temperature, but my heat is still increasing. And obviously past this point right here, you have straight gas, and there is no other state of matter after that. So a reversible process is like phase changes. I can go from a solid to a liquid, and I can go from a liquid to a solid, but the temperature stays constant. Okay, so phase change lets us change matter, particle movement, for a reversible process by adding heat, but the temperature stays constant. Okay, it's a very simple equation. Let's bust out those calculators, but I am going to say beware of the wording. So I am going to say that, little beware of wording, because they may try to trick you about the Q. So if I have elemental mercury as a liquid solid at room temperature, okay, so I'm just keeping track of some stuff, temperature, room temperature, okay, its normal freezing point. Well, freezing point, solid to liquid, liquid to solid, says that the temperature is negative 38.9. Well, at room temperature, it's a liquid, but when I freeze it into a solid, okay, this right here, so I'm going to put temperature for freezing, okay, negative 38 degrees Celsius. It's molar enthalpy of fusion. So this right here is called delta H, okay, and then sometimes you may see the little subscript fuse, okay, fusion. And no, I don't mean nuclear fission versus fusion. Fusion is a process, phase change, solid to liquid, liquid to solid. Okay, that's all it is. Okay, it says the word molar because notice right here it says kilojoules per mole. So it tells me that my delta H of fusion is 2.29 kilojoules per mole. What is the entropy? So I'm finding delta S of a system when 50 grams of mercury freezes at its normal normal freezing point. So it wants to know what's the entropy when it freezes. Okay, well, when something freezes, it's losing heat, and if something's losing heat, that means my Q is going to be negative. Okay, so how do I apply this? Okay, well, I know that my delta S, I need joules and I need Kelvin. Okay, so I'm going to take these grams and I'm going to start with those grams, 50 grams. Okay, now the reason why I'm going to start with those grams because look, they gave me delta H. They gave me kilojoules per mole. Well, if I go my 50.0 grams, and I'm going to put the molar mass of mercury on the bottom, and I'm going to put 1 mole on top. Okay, so we need, and don't forget to put mercury right here, we need the molar mass of mercury. We'll look it up in just a second. And then I'm going to keep this going because my grams will cancel. But I need my delta S, I need joules, but I have kilojoules per mole. I got to get rid of the moles, okay? So I'm going to do one more conversion. I'm going to put mole on the bottom, and I'm going to put 2.29 kilojoules on top. We did these conversions in chapter 5, okay? So reminder, these conversions, and I want to say it was 5.4, where we were doing stoichiometry with heat, okay? But notice it says freezes, okay? So because it lost heat, my Q is negative, which means my delta H is also negative. So I'm going to put a negative right here because of the word freezes. And I even gave you a hint. What happens to heat when you're freezing, okay? So this right here is 1 mole. So we need the molar mass of mercury. All right, so after looking at the periodic table, the molar mass of mercury, I have 200.59. Okay. So I'm going to, I got rid of my grams. I'm going to get rid of my moles. So I'm going to multiply and then divide. So I have 50 times that negative 2.29 and then divide 200.59. All right, so I get a negative 5 point, looks like we need 3 sig figs. Negative 0.57. If you want to go 0 or 1, doesn't matter. I usually round to the end, but we can round right now too. And I have kilojoules, but my delta S needs to be in joules. So I'm going to convert this into joules. I'm going to move that decimal 1, 2, 3. So I'm going to get negative 571. And then simply plug it into your delta S. Remember, delta S is your Q reverse. You could even say delta H over T. So I got the Q, I got the heat. Okay, so that's my Q. Negative 571. And then my temperature, I do need to get this temperature into Kelvin. So negative 38.9. Plus 273.15. It looks like I am going to need a number after the decimal. So negative 38.9 plus 273.15. And 1 after the decimal, I'm going to get 234. It says 0.25. You can put 2 or 3. It's not going to make a big difference, but that is Kelvin. And I'm going to put that number down at the bottom. And simply divide the two numbers. So negative 571 divide 234.3. And if we did it right, we're going to get that blue answer. And it looks like we did. Negative 2.44. I think I have 4.3. But remember, you're able to be off by 1. But your sig figs have to be perfection. Okay? So that's it. It's a simple, simple equation. So just beware of the wording, okay? Because just because the number looks positive doesn't mean that it will stay positive, okay? So the second law of thermodynamics says this about entropy. If it's a thermodynamically favored reaction, that we want entropy to always be increasing. Now we have something called delta S of the universe, okay? What delta S of the universe is, it's your system plus your surroundings. According to the law, we want movement, we want chaos, we want as much dispersion as possible. We want this value to be greater than 0 always, okay? As long as it's a thermodynamically favored reaction, aka spontaneous, okay? So if thermodynamically favored. So when is it reversible or irreversible? Well, so for an irreversible reaction, which means it's not equilibrium, irreversible, A makes B, we want that delta S universe, we want it greater than 0. But if it's not thermodynamically favored, that means it equals 0, which means it violates the law. We already know the law works because it's a law. But that means you are reversible, and that would be equilibrium, okay? So entropy is not conserved like the first law of thermodynamics. According to the second law, it says that the universe should always be increasing. So which means you are creating or destroying something to make sure that it's always increasing. Note that the second law of entropy of the universe must increase if it's thermodynamically favored. It is possible for entropy of the system to decrease if the surroundings increase, but it's got to be make sure that it's more than what the system decreased. So one of them can go up and the other one can go down. So basically your delta S of the system and your delta S of the surroundings, and you can abbreviate it sys and surround, they can be positive or negative. But the point of the law is when you add these two up together, it just has to be greater than 0 for the law to be valid. Okay, so I included an example with you. If it's thermodynamically favored, well, I'm just making a note. That means my universe better be greater than 0. The entropy of the system decreases. Okay, so my universe equals delta S of the system, and all I know is that the system decreased, it went down. If I add that to the surroundings, what do I know about the sign and the magnitude of the surroundings? Okay, well, according to the law, this has to be greater than 0. So if the system went down, that means the surrounding has to increase more than the system decreased. Okay, so if this went down 10 joules, this needs to go up by 11, okay, or 12 or 13. It just has to go more. So the sign would be positive, and the magnitude, it would have to increase more than the system decreased. Okay, plugging it in with actual math, if you have a reversible process, the surroundings undergo an entropy change of delta S surroundings. So I know my delta S universe is system and surroundings. But they did tell me something else besides this negative 78. They said reversible. Thermodynamic means that it's irreversible, which means if it's reversible, it's not thermodynamically favored, which means the delta S of the universe has to equal 0. Not increasing, has to equal 0. So what do you know about the system? Well, I know that the system, for this to equal 0, this has to be a positive 78 joules over Kelvin. Okay, very simple equation. The only thing is these two are not on your equation sheet. So make sure you know these equations. Same thing with your delta S. Doesn't really have a name for the equation, just for an isothermal process. Same thing, make sure you know the equation. Okay, add it to your equation sheet. Okay, one last thing, third law of thermodynamics, very simple law. A perfect crystal, which means if we have a perfect crystal, we're talking about a solid. Okay, at 0 Kelvin, not okay, 0 Kelvin, there is no translation, no rotation, no vibration, which means you literally have stopped movement. It's the only time you have no movement whatsoever. That means this is a state of perfect order, no particle movement, which means the third law says if it's a perfect solid crystal, your entropy will actually equal 0. Okay, which we know that is not thermodynamically favored. So it's only talking about a solid phase. You know, liquids and gas, they are moving forever and ever. Just some move more than others. But if you actually want to stop a solid particle movement, then you got to get it to 0 K. Okay? All right, short, sweet, to the point. See you on the next one.